Good morning. It's a pleasure to be here, and I want first of all to thank Ilvo and Flanders Food to invite me to give the introduction of this very nice, very interesting. To be honest, I'm very passionate to listen the next speaker also. So, but okay, now I will do my job. I will do the introduction. So my name is Vincent Baeten, and as it was yet told, I work at the Walloon Agricultural Research Center. And in fact, I am the scientific director in charge of the unit 12. The unit is quality and authentication of food products. Sorry, I had some problem with the pointer. So this unit, so the title is Quality and Authentication of Products. It's quite a young unit. We started this in 2020, in fact, and we merged different units together. And our goal, what we try to do, it's to help in the development and validation of methods to reinforce and assess the quality, but also the authentication of agricultural and agri-food products. Thank you. And so in this unit, in fact, you have now 6 different laboratory. And in this laboratory, in fact, all are based on different techniques. We have molecular biology, we have microbiology, microscopy. And we are also hosting the European Reference Laboratory for Animal Protein, but that will not be the topic of today. And so about 6 labs are dedicated to the use of vibrational spectroscopic techniques for different topics. In fact, we have the first lab was created in 89. It is the lab head by Bernard Leclerc until the end of this month. And then it will be Audrey Pissard. And there we have all the classical, I would say, benchtop instrument for the analysis of feed and food. Then we have another lab led by Philippe Vermeulen, where we are dedicated to the use of spectroscopic technique in the field, in the orchard, in the industry, also in the greenhouse. And the third lab is the lab led by Juan Antonio Fernandez Pierna, where there we are looking to data treatment. We are also looking to alternative technique like Raman spectroscopy, mid-infrared, and also imaging. But let's go a little bit about one point. For me, I'm very happy to work in spectroscopy since the beginning, in fact, because at the university I started there. And to be honest, it's always amazing and fascinating to see what's happened with photons, with the colors. In fact, when we see here the different leaves with different color in autumns, for instance, it's clearly the interaction between radiation and object. And what's fantastic is that how much we can use, how many information we have. What we use the light from the sun, the part of the light from the sun that reach us. And then this is the source. Then we use our eyes in order to be able, that our brain is able to transfer what we see in an information. Could be color, could be another thing. But in fact, the color are the resulting of the chemical composition and also in some aspect of the texture physical aspect of the object. And so if it's green, because a leaf is green today, it's because it's the part of the spectrum that is not the visible spectrum that is not absorbed by the plant. And if you look to a leaf, in fact, you will see that on the top, if you look from the top, the green will not be the same as if you look from the bottom, because in one side you look to the reflected light, in the other side you look to transmission light. So it gives you an idea how with just photons, the information we can bring. And so today we will not speak about visible, but we will speak about infrared. I'm sorry. Thank you. And here, as you can see here in this slide where we see the electromagnetic spectrum, the visible part is very small, and the infrared, it is the part of the electromagnetic spectra that is between the visible and the microwave. In fact, you have a different part there. You have the near infrared and the mid-infrared. You have also the far infrared that we call now more and more the terahertz domain. But okay, in the near and near, you have here the different frequency. And what is nice is that you will have different application. Okay, for the visible light, we use our eyes, our brain. For the infrared light, we will use spectrometer. That's what we do. And spectrometer, honestly, it's not a complicated instrument. In fact, if you open spectrometer, you will be surprised how many parts you have in it. It's quite simple, but it's not an easy technique. Infrared spectroscopy. There is different things that we have to manage and to be sure that we are on the right way. But with infrared spectroscopy, what you do, infrared spectrometer, you just put a sample in a dedicated sample holder. We'll see today also that you don't need. You can go directly to the sample also. And then you present, in this case, the cup to the sample, to the instrument, sorry. And then you will measure from the bottom and you will get the infrared spectra. So it means the absorbance of the object you present to the instrument at different frequency. This is clearly a benchtop instrument. But in this slide, okay, what we can see here, it's a little bit the slide we use when we want to present a little bit our history. Because in our institute, for the time being, we have more than 30 different near-infrared, mid-infrared, and Raman spectrometer. We have a lot of benchtop instruments. This is here, you can see different instruments that you will be dedicated for the laboratory, but we have also other instruments dedicated, for instance, for the factories, or that we can couple with fiber optics. And so this is for near-infrared, but since now 97, we are working also in the mid-infrared, because in mid-infrared, more and more it's coming a little bit later than the near-infrared, but in the food and feed, I would say, quality, there is also a big place taken by mid-infrared. And today we will have a talk about also the application mid-infrared in milk. Then quite soon, we look also to hyperspectral imaging. But it was in 2001. In fact, there was an instrument developed at that time by Spectral Dimension, used a lot in the pharmaceutical and in the chemical company. We had the chains with the support with, I would say, the federal, it was not the federal agency at that time, but let's say from the Belgium state, in order to get this nice instrument, the first hyperspectral imaging instrument, and we can apply it for food and feed quality control in the lab, of course. Then since that time, we are using other, and you will see that we go more and more also to go to the field. And today you will have different presentation when it was shown. After that, we have looked also to Raman spectroscopy. And this is something that you can see is that in the people working in food, I would say that near-infrared application is since decades. Mid-infrared also, Raman is coming more and more, and you will see that others are coming. And of course, there is something that all of us, we know what is booming. It is also the use of portable and handheld device. We started in 2008 with this, with one of the first one. And you will see that there is a lot of very interesting application. In fact, what you have to know, last year we make a survey and we find more than 70 companies selling near, mid, and Raman spectrometer. So just giving you, and you will see that today I'm sure that I will learn new. So that's a very, very important to see. One of the questions that the organizer asked me, it's to clarify a little bit what we call offline, at-line, online, inline. To be honest, here I have the slide. This is one of the slides that I present when I teach at the Catholic University in Louvain-la-Neuve, where there is also in all university a big interest to look to all these aspects. And here the slide is coming from internet. It's quite interesting because you have here in the central part, you have the process, let's say. And then you can have the approach where you have offline approach. And the offline approach is when you bring the sample to the lab. It's what we are doing since decades. But we can also have another approach is when you bring the spectrometer, let's say, at line, just on the side of the process. You can have also online when you make a bypass and then the sample go to the instrument and then go back to the line, or you can have inline or directly the sensor, it is in the line. What is important to be in mind here, it is that the fact that you have what is traveling, it's no more the samples, it's the data. More and more, it's the data. The challenge today in spectroscopy is really in the data. Of course, we have to do good analysis. You need to have good sensor given us a good spectra, but there is clearly a challenge there where we have to where the laboratory go to the sample. And this is not only for the process, for the industrial process. You observe this also in the field, in the orchard, in the greenhouse, and in the farms. One thing that we will see today is that we will speak about quantitative aspect and qualitative aspect. What is very important is to bear in mind that more and more the qualitative aspect is taken a large part and help a lot in the factories in order to check raw material. And we'll have a nice presentation today where there. And this is also something that is clearly booming, where more and more we want to use spectroscopy technique in order to say, okay, my batch is okay, or there is no unexpected thing. That's a good point. One of the things that was requested to me today to speak a little bit about calibration and okay. And so here I take a slide, quite simple slide. Calibration, it's not, as we can think sometimes, it's not complex. In fact, you have the spectra, you have the reference value, and then you will build a mathematical model. Of course, we have algorithm to do that. And what we use is algebra. But this is the calibration stage. When you have this model, then you can apply it on a new spectra and you will get a predicted value. That is important. The terminology is important. Spectroscopy gives you a predicted value. Why I insist on this? It is not because you have a result that you can be happy and safe. You have to check if the result it's in accordance, it's in compliance with what you expect. Because you have to understand that if you have a wrong model, if you have a wrong spectra, you will have a result, but it will be a wrong result. And that's very, very important. And so in all the steps, a very important thing, it's validation. And also when we speak to keep a model alive, we have to check the model all the time. We cannot say in one time, okay, I'm happy, I will not do nothing. No, no, you have to check. In order to illustrate a little bit what are the challenges today, I take challenge data. This is from a conference where we provide you a few months before the conference data. It was Pierre Dardenne, my former boss. He's now retired, but still working, as you can see. And here, the challenge is data, near-infrared data from peers, okay? And the purpose is to calibrate for one instrument and then to transfer the calibration to other instruments. And so I play a little bit with this data. The first thing we do when we have a new instrument, okay, and we want to look what we can do, we look to the spectra. This is here it's a transfer data, it's a derivative spectra. But okay, you look to that. We want to check what's happened. What you can see here clearly, for instance, that you have part of the spectra are very noisy. One recommendation, if you want to build a good model and then to transfer to other instrument, you have to be very careful to the spectra, and maybe, as it was the case here, to skip some part of the spectra because you will have some trouble when you will work after that. And then you build a model, and here you have in the y-axis the reference value, and then you will see what we get with predicted value. I put a line here, it is the perfect result. Let's say that my equation is perfect. And then I take this equation and we apply to another instrument. And what's happened is that this is for one instrument, this is for another instrument, this is for a third one, and a fourth one. As you can see, that we have quite interesting results because the grade that we can catch, I would say, the high level and the low level in terms of bricks in this case. But you can see that we have clearly a bias. When we have such kind of result using one equation built with one instrument and we transfer to the other, we are quite happy because as you can see, we have almost the problem we have, it's a bias problem, okay? And then what we can do, one of the things we can do, is we can make bias correction. And this is the result you get from the 4 instrument. And so there you can be happy because all your instruments in your factory will predict the same. And that's quite important. I repeat that another step important is that you still have year after year to check if this model is still working, because you can have new variety, you can have new condition, you can have a drift in the instrument, you have to check. And also when I say to check, it's to take samples to analyze by near infrared, and also this sample have to go to the lab in order to make the reference value in order to be sure that it's still working. This is something that it is missing, I would say, when we apply. It's that the check of the equation of the model, it's a continuous work. It has not been stopped. That's very, very important to be in mind. Sometimes the challenge could be different. You are working with one instrument during decades or year. In our case, it was 2 decades, and then suddenly the instrument is broken. So you have to think in what's happened with your database, because in near-infrared spectroscopy and infrared spectroscopy and other vibrational spectroscopy, key point is the database. I do not want to repeat the job I have done year before, and I do not want to lose this information. So we need to set up some strategy. Also, when we have handheld device, there is sometime interest to transfer the big database we have made in the lab in order to go to a handheld device. And this is what we see here. It's for an application, Apple application. You know that Belgium with our institute, but also the Catholic University of Leuven, we are quite, the team of Bart Nicolai and Walter Says, quite involved in analysis of fruit with near-infrared. And you can see that here we can do the transfer of database from the benchtop instrument to the handheld device. And this is something quite interesting. Another point very interesting, it is when we look to the network of instrument. And here I take an example from my colleagues working in the milk sector, because and we'll have a presentation today, the mid-infrared is used in the milk sector quite a lot. But here what I want to present to you is the difference we observe for different instruments in Europe that have analyzed the same milk. And so one lab, one instrument is in one color here in the graphic. And you can see that we have quite a lot of variability. I want to catch your attention that what we see here, it's the variation not due to the different samples they have analyzed. It's just the variation due to the instrument. And so what we need to do, it's a standardization. Because what we want to have at the end is that the master instrument is the instrument we have in our facility, for instance. We want that when we repeat analysis, all the points are in the center. This is what we have here in red. And then you can see in green, after standardization, the answer from the other instrument of the network. And in blue, it was without standardization. You can see that there clearly the standardization is important. Why we do that? Because when a network is doing that, and then the instrument are standardized, and here I missed to say something, is that there is different brands of instrument also, then after that you can share database, you can share equation. That's quite interesting because it could be quite cost effective to do that. So what we try to do there with the standardization process to try that all the instruments speak the same language. In the introduction, we have speak also about hyperspectral imaging. That is an exciting world. That's for scientists, it's magic. Because in addition to have with classical spectroscopy, absorbance according to the frequency, we have the spatial dimension. And that's very nice. It's a big challenge, but you will see today that there is very nice application. In our facility, we start, as I told you, yet several years. What's nice, we take the challenge a few years ago to bring our instrument and to bring them to the field also. So, and there we met our friends in our institute that are working with the spatial analysis, and then they come with the drone. But in fact, we are coming from the lab. So we try that to be sure that the answer of the instrument, the spectroscopic information is there, is what we do. And so we work very specific condition, and in order to be sure that we will be able to get the good spectra. And that's very amazing. We have to mention that here that Belgium, it's quite, with IMEC in Leuven, it's quite well in this sector because they developed very nice sensor. In the future, it's fantastic when you see what they are doing and what they will do in the future. And that's where we go. It's that the spatial dimension give us an opportunity. For instance, here we start to look to the detection of contaminants, for instance, and impurities, and also foreign bodies, for instance, in cereals. And here in these pictures, what you see is that we can detect different kind of impurities, different kind of botanical impurity. It could be also some defect, insect, unexpected product there. And that's what's very interesting. And in our case, for instance, we are able to detect more than 30 different impurities and botanical impurities, but also some other foreign material and so on, in one analysis. So that's quite interesting. But maybe one of the most interesting thing, at least in the laboratory, is that with such technique, we can address properly the sampling issue. You know, people don't like that, huh? But our main focus is on the quality and the validation of analytical data. You have to know that the error, the total error in all the measurement we are doing, it's 2 times bigger in the sampling step. So the most important part is the sampling step. And there, vibrational spectroscopy and definitely hyperspectral, but also handheld device, they have their place in order to help us to tackle properly. And so here you have, for instance, in green, blue, and red in the middle, I would say in the slide, you will see that there we have a result of online prediction where we have analyzed the serials in order to be able to detect ergot bodies. So in serial, what could happen? It's that we can have some contamination and development of ergot bodies. The ergot, it's not good for health, neither for animals or human. And in fact, because it's rich in alkaloids. And then there is interest in order to check. This is coming back because we had less problem, but with the climate change, for instance, that's come again. But here, what's very interesting, the challenge was to analyze at the ppm level. And the people say, yes, spectroscopy for ppm level, forget it. No, when you use hyperspectral imaging, you can do it. Because when you have a sample of cereals spiked at 1 ppm with ergot, it means that in 40 kilo, you have maybe 1 of 2 ergot body, no more. So when we receive in the lab from these samples 500 grams, you can imagine that the probability to have a positive sample is very low. And so here we did it, and we are able in 40 kilo to detect the few ergot bodies, so we can go to low detection with hyperspectral imaging. Another application we did, all this job is done mainly in European project, but it's also with Barilla, where they want to have a method able to check in the raw material the presence of common wheat, because what they want is to use durum wheat for pasta. Okay, and in the legislation, it say that it should be below 3%. Okay, so the present, but they go lower. They want to go lower because when there is common wheat in the process, there are some difficulties and they cannot assure the total quality, and so they prefer to go low. And here, what we have done, we have used hyperspectral imaging to do that. And what's nice with hyperspectral imaging is that you can use it in order to discriminate in this case and detect the presence of common wheat in durum wheat. My last slide here, I want to finish with a sweet, because we are in the morning, so a little bit with chocolate. That's, let's say, cacao beans. We have a small project, but quite exciting, between Brazil and Belgium, where we look to the use of hyperspectral imaging and handheld device also to check the raw material. You know, cacao, it's coming from Amazonian, and there they produce cacao beans, but not of top quality. And so what they want to do is to be able to improve the quality. And for that, they need the tools that allow them to check if the fermentation is okay, to check if material, when they have the raw material, there was no mixing between well-fermented product and non-well-fermented product, and also to check what is the hybrid. And here you have one of the recent publications we have done in that field. All this stuff, the spectroscopy has also the place in the traceability challenge and authentication. This is really, really hot topic for the moment in all the product chain and so on. And with that, I finish. I want to thank you, bedankt. And no, I'm ready for your question. And you know, Jean-Blou is not so far away, so you are always welcome in our lab to discuss photons, of course. Thank you.